Hello, my name is Chancharik Mitra, and I'm excited to present compositional chain of thought prompting for large multimodal models. My co-authors are Brendan Huang, Trevor Darrell, and Roei Herzig, all from the Berkeley Artificial Intelligence Research Group. To start off, vision language models excel at many tasks. These include everything from VQA to image text retrieval. However, even the current state-of-the-art VLMs, large multimodal models, struggle with fine-grained compositional visual understanding. A few examples of such tasks are shown below. Now, the question as to why these VLMs fail is for a few reasons. First, most images are easily distinguishable by their objects. However, in tasks that deal with the attributes or complex relations between these objects, VLMs would struggle to understand those complex attributes and relationships because they are not present in a lot of the data sets that are used to fine-tune them. Many of these data sets simply stop at having simple image caption pairs, which wouldn't be helpful for an example as shown on the right, for example. And so to remedy this, we would like to use perhaps a different representation than captions, maybe scene graphs. So scene graphs are dense compositional descriptions of images, and they contain attribute and relationship information that we want to be able to solve these tasks. However, the challenge here is that there aren't a lot of scene graphs, and these annotations are costly from a human annotation perspective, more so than captions, of course. And so we remedy this. To use scene graphs in our method, we present a zero-shot prompting method leveraging scene graph generation for enhancing LMM's compositional visual reasoning. At a high level, we generate a scene graph that we then use to produce an improved response to the question that includes compositional understanding. Some representative related work includes zero-shot chain of thought, a language method, multimodal chain of thought, which requires fine-tuning, and DDCoT and vidIL, which reasons over the text captions of images and video, but not the image directly. And we also use scene graphs, which is another differentiating factor. Okay, let's provide a detailed view of our method. So our method consists of two LMM calls made during inference time. So no fine-tuning is required. So during the first LMM call, we provide an image as well as the input task, followed by a scene graph generation prompt, which includes requirements for what the scene graph should include, such as the objects, attributes, and the relationships that are specifically relevant to answering the question. The LMM outputs a scene graph that is then used in the second step, where once again, we pass the image, the generated scene graph, the question or the task, and finally an answer extraction prompt based on the format of the task. In this case, it's a multiple choice. And so given this, the second step, the LMM produces a response to the question with the context of a scene graph. So I guess one way to view this is that LMMs have compositional LMMs are generating scene graphs. So we bypass the problem of obtaining annotations, and also our method is a prompting method, so it does not require fine-tuning. So it avoids issues of forgetting as well as like compute costs and things of that nature. So it's a lightweight method of making LMMs more compositional. And as we'll see, this also improves performance on general vision and language tasks. Okay, so in our experiments, we use baselines of Lava 1.5 and Instruct Blip. And we also evaluate on data sets that include multimodal reasoning benchmarks and compositional VL benchmarks. There are a few more that we evaluate on, as we'll see in our results. So in addition to Lava 1.5 and Instruct Blip, we also evaluate on Sphinx and GPT-4. And we find that our method, CCoT, improves over the zero-shot capabilities of these models on multimodal and compositional benchmarks across the board. And indeed, in many cases, and in almost all cases, we also improve upon zero-shot chain of thought, which itself actually degrades performance on these benchmarks. So as you can see, for example, on InstructBlip and Lava's SeedBench and MMBench results, standard language prompting methods are maybe not beneficial, but rather CCoT, which is specifically designed for vision and language, and as well as considering the compositional information in image, is beneficial across the board. We provide a few examples here of, failure and success cases on different benchmarks, ranging from SeedBench, MMBench, as well as WHOOPs. And so now our conclusions. So our prompting method is zero shot, so there are no need for few shot examples. And it also generates its scene graphs, so it doesn't require any ground truth scene graph annotations. So we find that scene graphs, if used correctly, can enhance not only compositional visual understanding, but general multimodal capabilities in LMMs. We're excited about this work and how it can be used in the future, either the method itself, as well as the generated scene graphs and downstream tasks. And with that, thank you so much for listening.